Welcome to Jelly. Today we are diving deep into the realm of sovereign data, into encrypted data. We are going to architect what I call SharkGuard. It is a Sting key generator designed to protect your data and your client's data. In the current climate, most AI applications leak intelligence. They're drifting aimlessly in the cloud, and they're relying on third-party permissions just to exist. We're doing things differently. I'm teaching you how to architect SharkGuard. It is a local first module, which just means that it's going to run independently on your own hardware. It's also hybrid ready, meaning we can connect this to the cloud without being reliant on it. Today, we're not just writing a script. We are growing an apex predator that's there to protect and watch over your own data and the data of your clients. We are going to marry the sensitive client intelligence directly to your physical hardware. We're going to ensure that your sovereignty remains intact even when you surface to make contact with the hybrid cloud. You could follow along and build this for free. Before we grow some teeth, before we get protected, before we add the encryption, let's look at the habitat. Let's look at the tools that you're going to need in order to support this build. In order to deploy SharkGuard effectively, your environment needs to be as hardened as the code. And so here's the stack we are using today. We use the Linux terminal because it offers a direct hardware level communication required for a true Sting key. We're also going to use Visual Studio Code, and this is where we're going to bridge the gap between human intent and machine execution. You're going to need Python 3.10 or greater. The Shark is built on high performance Python. That's going to allow us to move fast while maintaining the industrial grade encryption that we want. And we are going to install a external library called Cryptography. We're going to need this because this is going to give us the AES 128, which is a Fernet engine, and that's going to serve as the mathematical teeth of our predator, which is going to protect our data and encrypt our data. In the Jelly Syndicate, I call this a Sting key, but in a security manual, you'll find it under Symmetric AES 128 encryption. We chose this standard because it's the high watermark for local speed and security. It's what banks and sovereign entities use to harden their internal vaults. Most people use a password like password123 in order to encrypt things, but that's a weak tooth. A Sting key is generated by the computer's hardware random generator number, and it has randomness, making it mathematically impossible to just guess on a whim or to just brute force your way in compared to a human password, which is much easier. The traits of a Sting key or this level of encryption are that it's hardware bound, so it's on your own device. It's generated using entropy of your specific CPU, randomness of your CPU. It marries your data to that one piece of hardware, that one thing that you're using that on. So you don't create it. The Shark that we're going to build today does create the key itself. The first time you run the software, the Shark will pulse the system. If it doesn't feel a key, it will grow a new one instantly. And then it's hidden and shielded. So we'll use a dot prefix at the beginning of Sting key. This way it will stay invisible to casual observers, and it'll be protected by your git ignore. You're going to want to download Linux, Ubuntu, and you're going to want to add WSL to your Visual Studio Code. You're going to want to download this blue version of Visual Studio Code if you don't have it already and you're actually trying to build this. Those of you who are familiar with Linux, then you'll understand easily what I'm talking about. Those of you who are less familiar with Linux, who maybe are a little bit more scared, it gives you more control over the hardware. I need to clone my GitHub repository. First thing that we're doing and that I just did here to begin our project is I cloned my GitHub repository by typing in git clone, which says, hey, get the skeleton of this repository. I typed in, as you can see, my URL, and JellyWorks Offline is my GitHub. And then you clone this, then we also want to create CD SharkGuard, which is the folder that we're going to have on the desktop for this repository. We cloned it. GitHub on my desktop wanted to talk to Visual Studio and make sure that I verified that I was actually the one accessing this. And then as you can see, everything went through and we are all set. The first thing I did before I started this was start a git ignore and use Python because I'm using Python. And then I added other functions to the git ignore that made sense, and I could share that with you later. We're not creating the SharkGuard class in Python just yet. What we're now going to do, now that we've cloned our GitHub repository, we need to type in Python 3. What we typed in here is Python 3 venv.venv. What we're doing is we're creating a virtual environment, and we want to ensure that our Shark has its own dedicated water to swim in. We don't want it mixing with other folders and other files and other projects. We want this thing to be fresh and contained within its own environment, within its own habitat. That was successful. And now what we're going to do is we're going to type in source venv-bin activate, and this is the specific script that's going to turn on the virtual environment, and then it's going to shift our Python path to our clean room that we are created. And there it is. Once you see that parentheses in the left, .venv, virtual environment, that means we are good to go. Now, before we can create our SharkGuard, we also have to install the library that I told you about. And we're going to do a pip install cryptography. Encryption is heavy math, and we have to install a separate library that Python doesn't natively come with. And that library is cryptography. It uses C code, and then this gives us the speed of a low-level language with the ease of Python. It's essential for the high performance that we need for this build. Now we're just going to check our git ignore before we start building out the SharkGuard to make sure that if we build our SharkGuard that our key doesn't accidentally end up on our GitHub. So we need to have that .sting key or .sting.key show up when we hit this button. @sting just stands for concatenate, something I'm probably pronouncing wrong. But basically, all it's telling Linux to do is, hey, print this file on the screen. And there it is. Now we can see the git ignore I was talking to you about. And we scroll up to here and we see .sting.key. Perfect. Now we know that we can safely create this key and it's not going to be leaked onto a repository that's online. So as you see, I put touch sharkguard.py. That created our file. I went to file open sharkguard.py. That just means sharkguard.python file. And now we are going to code our class. So we start with import OS, which means we're just going to import our operating system, lib import. And then we're going to do from cryptography.fernet, import fernet, and invalid token. And from pathlib, we import path. The reason that we do that is because path treats a file location as a living object and not just a string of text. From cryptography.fernet, we import fernet and invalid token. Fernet gives us the implementation of AES 128, which is the encryption that we want to use. It handles the heavy math so we can focus on the logic. And then we have to have invalid token because this is the error math that the engine throws if the key doesn't match the data. So we're creating a class, sting key error exception. So we are using sting key error just to create a child class of the built-in exception. And we put this pass under here just to basically tell Python this class doesn't have any extra logic and we're just using its name. That's where the power lies. Now we get to our main class here, which is SharkGuard. The colon that we put just tells us, hey, look below. The init is the constructor. It's going to run the microsecond that the shark is instantiated into another file and run. And then we put self in there because it represents the specific instance of the shark. It's how the shark refers to its own body. And so we set a default name. The dot prefix right here is important. The fact that we put a dot before sting.key. This is a Linux or Unix standard because that's going to make the file hidden, which is important because we don't just want anybody clicking on this key or messing with this key. It could ruin data, or it could cost you your ability to view data. The file is important here. Self.basepath equals path file. The file is important because it's a special Python variable that contains the path to the current script that we're writing. The parent right here, this moves the focus up a single level to the folder containing the script that it's in. And then this resolve is pretty important because it strips away any relative links and gets the absolute hardware address, and this is why it works on any computer. This slash right here, this // is overloaded to act as a path joiner. So it intelligently fuses the path and the file name together, and that function's coming from pathlib, which we imported at the top. With self.byte equals self.check pulse, we are calling our terminal heartbeat method, and we're going to store the result in the self.byte, which is the key. Self.engine equals self.byte. Now we're going to pass the key into the math engine. Self.engine, Fernet is the key, self.byte is the key. Fernet is obviously the thing we imported, which has the AES 128. And then this is now basically arming our shark. So what did we just do there? The file is the most important part of this because it gives the script a sense of self. And by calling .resolve, the shark anchors itself to the physical location on the hard drive, on your hardware. The / isn't doing division here. It's not doing math. It's joining paths because it's joining the hidden sting key. And once we run check pulse to find the hardware signature and then arm the Fernet engine, now the SharkGuard is alive. So now we add the check pulse and bytes right here. This is a type hint. It tells the developer and the machine that this function is guaranteed to return raw binary data. If not self.tooth_file.exists, we're going to check the hard drive. If the file is missing, the guard clause triggers. Tooth equals Fernet.generate_key, which is us checking the hard drive. Shark's going to check the hard drive. If the file is missing, then the guard clause is going to trigger. And with tooth equals Fernet.generate_key, we're going to talk to the CPU, the hardware's random number generator, to grow a new 128-bit key, hence AES 128. With open self.tooth_file, WB, meaning write binary, as F is a format. With is a context manager. It ensures the file is closed safely, even if the program crashes. WB, like I said, stands for write binary. We aren't writing text. We are burning raw math. Write tooth, return tooth. F.write tooth with those lines of code. Write meaning we're pushing the bytes onto the disk. And then with open self.tooth file, read binary this time as F. So with that right there, we had it write binary to the drive. And now we've also had it read the binary. With the check pulse, the bytes, we're being very clear about what type of data this is. And the if not statement right here, well, this is our guard clause. If the shark doesn't feel a tooth on the hardware, then it's going to generate one. Fernet.generate_key. It's going to grow a new tooth. We use the with open context manager with the write binary. We're burning really raw binary directly into the drive. If a key already exists, we use read binary, because if one already exists, we want to read and see that it does. And then we're going to grab that key. That's how the hardware and the SharkGuard are working together. And this is making your data sovereign, putting it in your own hands and keeping it safe for you right on your own device. Fclamp self raw data bytes self.engine.encrypt raw data.encode. And what we're telling the shark to do here is to take the human readable string STL. We're having the math engine self.engine take the bytes and the key and encrypt it, making the sovereign noise. With raw data, like we just said before, we're taking the human readable string and we're encoding it, because computers don't encrypt letters, they encrypt numbers. So .encode turns human text, which is the string, into UTF-8 bytes so that the engine itself can process it. We're going to use try, this is our hardened loop here, with decrypted output. If the encrypted clamping function turned a string into something that was not readable, then the decrypted function is going to turn it back into a readable string when you have access. We're going to return the decrypted output, except for if we have an invalid token, in which case we are going to raise the sting key error we put at the top. So we want to, if something's wrong with the key, we want to have an invalid token error. The sting key error is going to say the hardware tooth does not match this data, access denied. That's pretty self-explanatory. But these are the final things that we have inside of our code, which is the clamp and release, to encrypt and decrypt data, to keep things protected and to allow you access if you have the key, or to throw up an error if something goes wrong. So we're using these triple quotation marks to give the code a voice. These are doc strings. We want to add them in so that it's production grade and you can just hover over a function like clamp and it could tell you exactly what it does. Look at how I defined self.basePath. We aren't just using a basic file name anymore. I'm using pathlib, the library that we imported at the top top in order to resolve exactly where this script lives on the hard drive. So most scripts will break if you run them in the wrong folder, or if you run them from the wrong folder in the terminal rather. So the Shark doesn't. This SharkGuard is not going to break, and by using resolve, the Shark anchors its tooth to its own home folder. Whether you're on Linux, Mac, Chewy, Windows, the Shark is environment agnostic. It knows what habitat it's in, and regardless of the operating system, it can function. And I've added type hints like bytes. This tells the computer exactly what kind of artillery to expect from each function. It prevents the physics errors before they even happen. This is how you architect for 100% uptime. Now we have to test this code out. We're going to type in the terminal touch feeding test.py. We're going to open that file. Now we have a fresh block of Python code to code. And now what we're going to do is create the test script. So from SharkGuard, import SharkGuard, and the sting key error. We want to reach into the file that we just created. We want to pull the predator class out, the SharkGuard, and the alert system, the sting key error, in case something goes wrong, so that we can test this thing out. So we build this engine once, and then we just call it into any bay or any ocean that we need whenever we actually need it. If name equals main, then we take our shark, which equals the SharkGuard, the class that we just put in there. This brings our shark in here and says, run this with these parentheses right there. So we're going to define prey, top secret, $10,000 client game plan or client information. We had high level client and their info was right there. That's the thing that people would be trying to access. So we put that in there. We're going to format it, surface data. The if name equals main. This is the ignition switch, so we're going to run this thing. It tells Python to only run the code below. So I'm running this specific file directly. It's going to keep our tests from running accidentally when the shark is imported into your future applications or into your future software projects or into any folder where you need protection. The shark equals SharkGuard. This is the instantiating that I was talking about before, where we're taking the shark, we're putting it here, and then we're creating a live object in the computer's memory. So the moment that this line runs, the SharkGuard, the shark's init triggers, which is, if you remember at the top of the functions inside of the SharkGuard, then the hardware pulse is going to happen. The shark's going to sense out for a key. Sting key is either going to be gripped. If it's not there, it's going to be created. If it's missing, there's going to be an error. We're obviously going to try to get the top secret $10,000 client information, which is just a string that we wrote here. That's all we'll see because we're just testing. This isn't actually data that's locked away. This is the data that we're trying to see if we can get. So this is our intelligence. It's the sensitive data we want to vanish from the surface if we don't have the key. And then we're going to use this F string right here because we want it to show the data in its unprotected state before the attack. What we just did here is shark's gonna try to clamp on the prey right here. And then we're only going to get back an encrypted blob, and we're only going to get back the first 30 lines, or the first 30 characters rather, of this blob. We call this a slice, it's colon, this 30, and clamped.decode. It's going to turn the raw binary math into a readable string of gibberish, just nonsense. And the 30 is going to ensure that we don't clutter up the terminal and overwhelm ourselves while we're testing. Print, initiating, store. We're going to use try because we're telling Python to attempt to run this code when we expect the string to be there. The result will be that the shark will release what is clamped, and it will print the restored nutrient, and it will give us the result, except for when there is an error, as E, general system failure, E. At our try function, we prepare for the things that could go wrong. Obviously, if you have the key, the shark will release it, and you'll get the result. We have the sting key error. If there is no key, if the shark finds out that we have the wrong key or that we're missing a key entirely, then we get an error that the tooth is missing or something's wrong. And then our accept exception, this is the ocean guard. This is catching any random failure like a hardware crash or a memory leak, anything that isn't related to our sting key. And we just want to print that out so that we can diagnose whatever the physics of the crash was. And this is really just us architecting for reality. We wanted to create a hardened loop. And this is where we are expecting the hardware handshake to succeed. But the accept block is our shield. If we move our sting key, then the program won't just give me a messy wall of red text. It will actually catch the error and it will actually show me what's going on. And this really just takes our code to the next level and make sure that we can heal any problems or be aware of any problems that are happening. Now, so we've saved everything, checked my code. If you are following along, then I missed this / here with the N, and I accidentally put string key error instead of sting key error, and I added sting key up here, which is not a class. I don't know why I did that. But if you're following along, you have to correct those things if you want to actually run this feeding test. And if you're watching me, it's late and I also forgot to put a colon at the end of the function here, the def init. And if we didn't fix that, then this thing's not going to run. As you can see here, we have my shark generated the key. And after a few syntax errors were fixed, we got this correct. And now we know our code is working. That's what the terminal is for. That's why we built these things in here, so we can see exactly what might be going on and going wrong. We now know that the shark generated a key, so that we had the key, and then gave us the surface data. As you can see here with our encrypted blob, that took our plain English and turned it into AES 128 binary, but it's invisible to the human eye. We used .decode, which forced the math into a string, and we only slice the first 30 characters of that string. The data is no longer human intelligence. It's now sovereign noise. Even if this file were intercepted right now, it is mathematically worthless without the hardware shark tooth that we just generated, the sting key. This restored nutrient line right down here actually proves that we called on shark.release clamped as we wrote it, and the shark reached back into the local drive, matched the mathematical signature of this sting key that it had just created, and reversed the randomness in order to give us the top secret $10,000 information. And we did all of this without sending any data to the cloud. This all happened locally. This all happened on the hard drive. This all happened without any APIs or anything else reaching in and getting access to our intelligence. Now we're going to move our sting key. Actually, it still just generated a new key and then gave us the information. But what we want to have happen is to see what happens when I try to crack it with a different key. For that, we're going to have to create another demo. Touch Amputation Demo.py. And now we'll open that file. We're just going to quickly code another test here. Bring in the SharkGuard. Something restore with mismatched use intelligence print. All right, now that we have our demo all done up, there we go. We attempt to restore with the mismatched tooth. We got a syndicate alert, which is what we want to see. The hardware tooth does not match this data. Our access was denied. There it is. That means that our shark is working perfectly. That access denied right there proves that the shark realized that the habitat didn't match the intelligence and shut the door. And this isn't a crash, it's a vault that knows its own master. This SharkGuard layer, you have the engine, the habitat, the shield, you've got everything right here. So now we're going to try to remove the sting key to see that the shark actually realizes, we already saw, that the key is not there, and then goes to create one again, which we can look at feeding test.py, and bam, it created its own key again and healed itself. And now, if this wasn't a Python script, if this was real data, we would not have access to any of the data that was attached to the old key, even though it generated a new key. We aren't just hiding data. You can see from these tests right here that we're marrying the data to the hardware, and that if the shark doesn't feel like its tooth is there, then it shuts the door. If it feels like the tooth is missing completely, or if you're trying to use a different tooth, it shuts you down. If it feels like the tooth is missing completely, it generates another one. So you have the full architecture right here for SharkGuard Layer 1. You have the engine, the heartbeat, the emergency protocols. We just ran the tests, and the clamp and release methods work perfectly. We successfully turned intelligence into noise and then back again. But what we just built is a silo. It assumes everything goes perfectly. It assumes the user has the right libraries installed. It assumes no one moves the file. And worst of all, if the key goes missing, it just auto-generates a new one and locks us out of our old data forever. If we're going to use this in a live production setting, or if we're going to give it to our clients, we can't have some amateur hour security build here. And because a web browser can't answer a terminal prompt, I need to update and upgrade this script into something that's more production ready. We're going to add hardware DNA. It locks the physical hardware or the physical machine itself. We're going to add a self filter so that it cleans its own environment. And we're going to add a 3 tides recovery system so we never lose our data. Let's open up SharkGuard and let's upgrade this line by line. We are going to delete import OS. We're going to replace them or replace it with 4 new tools. Import subprocess, import sys. This is going to give Python the ability to type into its own terminal. And with platform and uuid, it gives the script eyes to see the physical hardware it's sitting on. Right beneath the imports, I'm adding a function called tank filter. If you have a jellyfish in a tank, then the water has to be right. This is going to be our self-filter protocol. If a client downloads our Shark and doesn't have cryptography, which is a library that we need installed in order to use this key, then this code catches the error for us using import error and using subprocess, which we imported at the top. And it silently runs a pip install in the background of the program, filters the tank and prepares the environment before the software even starts running. So in our init function, we're going to keep our pathlib anchor as you see up top. But before the shark takes its first breath, we're going to call in our tank filter, cryptography, and this is going to ensure that our shark's armor is in the water with us, no matter what hardware we are on. .dna equals self.getHardware. And so we're checking for what kind of system we're on, and we're getting that DNA so we know what libraries to install. With check filter, we're just going to check if there's a key or not. Does it exist or not? We're looking into folder and we're seeing, does the protection exist with that number 4? We're pulsing for it. With open self.tooth_file, we're going to read the binary. F. Cool. If you look at the bottom of this init function, I removed all the old self-byte logic because if the key is missing, we don't want to just auto-generate some new key and overwrite our old vault, because if we check the status and it's healthy, then we just mount the engine. If it's not, we wait for a human in the loop to make a decision, which is much safer and better for your data than the shark just deciding on its own to create new key after new key and you losing all of your data. We've upgraded with that. Senses the unique MAC address. We created a new method called getHardwareDNA, and this is using uuid.getnode, and this reaches down to the motherboard and it pulls the physical MAC address of the network card. Basically, we save this to the self.dna, and our encryption is now tied to the actual copper of that specific computer. That means that the shark is now locked to the physical hardware and it's filtering its own tank. But we have a major problem left to solve, which is the pulse check. In my old script that you can see here, if the shark couldn't find its key, it just silently auto-generated a new one. And that was dangerous because if you accidentally move your key, if you accidentally move your folder that has it in it, then the shark just overwrites your old vault and your data is lost in the deep forever. We don't want to do that. And the old script was actually terminal locked. What we want to do here at Jelly is we want to build offline first technology. We don't want our clients relying on external cloud APIs, but we do want our code to be universal. Whether you are wrapping this in HTML or CSS, and CSS for a desktop app, if you're building a local web app or you're white labeling it for a client's brand, then the visual dashboard cannot talk to a Python terminal. And so we need to replace the terminal lock with a universal local bridge. So we're going to silence the shark so it acts as a pure local engine. And then we're going to build 3 tides, which are going to be 3 distinct manual ways to recover the data And we're going to do it all completely offline. Let's highlight our check pulse method and delete. Let's start fresh. We're going to check tank pulse. We want to return the state of the tank to the UI. Wrapper ready. If the file doesn't exist, we're going to return a void. We remove the auto generation. Instead of the shark panicking and making a new key, which we were doing last time or earlier, our shark is just going to check the local hard drive, and it's going to give us back one of these answers. It's either going to be not there, void, or it is there and is healthy. And we want to return strings, these things in quotation marks, because when we look this up in our HTML later, the JavaScript can read that word void, and it's going to give a nice aesthetically pleasing pop-up that says, hey, the vault is not found in the tank. How would you like to proceed? And then that's how we build for any type of user interface. So the shark does the math, and then the front end handles the conversation. And then you don't need the cloud or any of that. Now we are going to create our tides. So first tide, the first level of security that somebody can choose is tide anchor, which we just created here. If the user chooses this, then it basically just does what our old script did. It grows a brand new tooth and saves it locally. And then if you actually lose your key, then you're pretty much screwed. But if you want that level of security, it's available. And it's totally the user's choice. Both.engine equals Fernet tooth turn tooth.decode. With tide drift, the second option, it's going to still generate a new tooth as you see up here with fernet.generateKey, but it sends the raw text via return tooth.decode back to the dashboard so that the user can copy it and save it to a physical piece of paper or an offline USB drive or somewhere where they can back up their key and not lose all their data in the event that something happens on their hardware and it goes missing, or somebody moves the file, or it gets damaged. And our third is def tide sonar, self, try tooth equals DNA, seed.encode, return restored, accept exception, return fail. With these three tides, since we removed the auto generation, we have to give the recovery power back to the user on the front end, and that's what we just did. And with this third tide, tide sonar, this is our hybrid option. It requires a DNA seed, and if a client's hardware crashes and they get a new machine or their vault is locked, but with sonar, they can paste the text seed they saved earlier right into their dashboard. And the shark will validate it, accept it, and it will regrow the exact same tooth. That will mean that the data will be recovered, the client will be saved, they won't have to worry about it. Other cool thing about this is that we're achieving it with completely offline first logic. The reason that this is called the Remora is that a Remora is a little fish that attaches itself to a great white shark. In our ecosystem of the Jelly ecosystem, your phone, your USB drive, or your piece of paper is the Remora, right? And when the shark generates your DNA seed during the tide drift, in our Jelly ecosystem, your phone, your USB drive, or your piece of paper can be the Remora, and when the shark generates the DNA seed during the tide drift, it is going to hand the key to the Remora, and you take that Remora and you put it in your pocket. If the great white ever dies, your laptop crashes, or something like that, then you just bring the Remora to a new laptop, you plug the seed in to the tide sonar here, and the shark can be reborn. So you can also choose that method of security. So you don't need a cloud server to have a backup plan. You're just holding the backup in your physical hands or in a vault or something like that in a safe. We've removed the terminal lock. We've built our three tides, and our script is completely UI agnostic, and it's ready to plug into the offline dashboard. But there is one final architectural flaw that we have to fix because we stopped the shark from auto-generating a key. And it is entirely possible that the shark wakes up in a void. And if our front end accidentally asks a void shark to encrypt data, the program will crash because there's no encryption engine mounted. We need to add fail-safes. And once we do that, I'm going to run a live demo right here in the terminal to show you exactly how the Remora offline seed works and how to cryptographically destroy it. So def clamp data, if not, has attributes, self engine. We want to raise the sting key error. I'm going to return self.engine.encrypt raw data.encode. We're just checking if the shark has a key. If it doesn't, we're going to throw up an error and we're going to allow the user to choose which of the tied options that they want. If the shark doesn't have the tools that it needs, meaning the key, then it says, hey, you need to pick what option that you want if there's a void. Remember, we're going to convert math back into text, that blob back into text with our release method, because if we have the key, there's no attribute. The shark is disarmed. We're going to return self.engine.decrypt, encrypted blob code, accept invalid token. I changed the accept block to return error. Instead of crashing the program, we're just going to return an error message, and the Java will be able to display this, or the JavaScript will be able to display this to the client via the interface. All right, we built the architecture, but we don't just write code, we prove the physics. I'm going to run a disaster recovery simulation right now in the terminal. Let's just read the terminal real quick so you can see exactly what happened. It was executing the tide drift. It gives us the Remora seed, which you can see here. Imagine I just copied this Remora seed to a USB drive or into an encrypted node on my phone. Now, we have a fatal hardware failure that happens next. We wrote a line of code in the test script using unlink, and that reaches into the hard drive and permanently deletes the .sting.key file. The local vault is dead. What we did was then we simulated a system reboot. So the shark wakes up, it checks the tank, it reports the void. If this was a standard offline app, my data would be gone forever. But because we don't want to lose our data forever, we have the Remora seed. We injected the Remora seed back into the shark. And then the sonar status said, hey, that's acceptable, and it restored it. So we brought back our data, and essentially we just survived the total hardware wipe without a single call to a cloud server, an API, or a database. You hold the key, you own the hardware, and you get to decide what level of security you want, rather than the shark just going rogue and deciding to create keys and destroy data forever. As you can see, we did run our shark from SharkGuard. We imported our SharkGuard. That's what was running through here. We woke up the shark and then the system executed. And by using shark.toothFile_unlink, we delete the local key because we said missing OK equals true. This deletes the file. It's the pathlib way to delete the file that we imported into our SharkGuard that you saw, pathlib. We're not just making up variables. We're not just pretending to run the script. We actually ran the shark. We saw that we actually destroyed the key. We actually simulated a system reboot. Then we took advantage of our tide sonar in order to restore our key using the Remora that we had set up. And then we regenerated our data. If I was actually going to use this key, and you're thinking, well, you just broadcasted this key in the terminal because you saw the Remora seed was generated. It gave me the key right here, which I can copy this text. I can drop it into a USB drive, like I said. I can write it down into a notebook, which may not be the wisest thing because capital letters, if you get something wrong, you're completely screwed. You may just want to copy it into a separate drive or put it on your phone or somewhere more secure where this is actually going to be the key. But if you accidentally put up your encrypted data on a screen like I just did, and you don't want everybody to see it, we're going to do a cryptographic key rotation. Our Remora seed was exposed on video. Want to mathematically eliminate the old seed. Do computer shark.tide anchor overwrites the recovered key with the new one. It allows us to keep our data in the process. We just switch it out so nobody has your stuff. All right, so the old Remora is now transformed. Python Remora. As you can see at the bottom of this terminal, we executed tied anchor. We got rid of the exposed seed, and then a new local tooth was anchored, and the old Remora is now transformed. That's it. That's how we protect the data. And now whatever was generated up here is now transformed down here, and you can't get access to my data. Now, obviously there's nothing else in this file, so it wouldn't matter because I'm just building it, but you get the picture. That is how you build an AES 128 Sting key and make sure that it can be used on any hardware with any front end without crashing, without dying, environment agnostic, has the human in the loop, has all the systems of recovery, and you get to choose. I mean, if there's anything else I missed, feel free to leave it in the comments. If you like it, feel free to leave it in the comments. I'll be doing more builds like this online, and if you enjoyed this, please give it a thumbs up, subscribe to the channel. Let's build some cool stuff together. I think it's pretty cool being completely offline, protecting your data yourself, and protecting your client's data, and making sure that anything you need encrypted and decrypted, you have the ability to do that. You're no longer just viewing from the sideline. You're an architect of sovereign intelligence. I'm giving this full assembly to you. If things go down, if the grid's not functioning, your data is not only safe, but you can use it and leverage it. You don't have to slow your workflow down. You can have operations running on your own hardware, and you're not going to be dependent on the cloud, but you can link up to it and use it if you want as an asset. But if it's not there, you're not going to be out of business. That's the goal: sovereign intelligence, sovereign systems. And it starts with having your data and your client's data encrypted, which is why we started right here. Hope you enjoyed that. Let me know if you have any questions in the comments. Let me know what you think about this build. If there's anything I missed and you'd like to add in, look forward to hearing your feedback.